Hi everyone. Um, Today I'll be giving a presentation on my paper titled Cascaded Solid State Transformer Structure to Power Fast EV Charging Stations from Medium Voltage Transmission Lines. So the content of the presentation is introduction, followed by the different EV chargers and medium voltage fed charging stations. And then we would be discussing SST embedded EV charger, which is the proposed configuration, followed by the simulation results, and finally I'll be giving the conclusions. So we know that transportation and energy sector are the two main consumers of fossil fuel based energy. In transportation sector, the consumption of fossil fuel provide benefits such as no raging anxiety, high energy density performance, and matured technological advancements. The different alternatives that are under development are namely electric vehicles, hybrid electric vehicles, and fuel cell based vehicles. Especially in electric vehicles, performance and driving range depends entirely on the battery storage. Although there is significant progress in the last decade, which led to the cost coming down, same by approximately 10 times, and it is possible to achieve higher power densities, but still it is inferior to fossil fuel based solutions, right? So when we are using the energy storage, this results in range anxiety, comparatively inferior acceleration performance, and higher battery charging time. Among these factors, charging time is identified as the major hindrance for wide acceptance of electric vehicle in the commercial market. And restriction on the charging current imposed by the C rating of the battery is another factor. So to address these things, many manufacturers have come up and researchers have propose different charging methodologies and control strategies so that we can pump large amount of power into the battery. And the final vision is to make this charging experience same as that of a gasoline refueling station, right? So the different battery charging methods are the first is most popular constant current and voltage method, which is widely acceptable, simple in control. Battery voltage is controllable at cutoff voltage. The next is a constant power charging method, wherein you try to keep the power constant, but this is complex, and the advantage is there are no issues with respect to the thermal management. The next is multi-stage constant current method, wherein the current is controlled at different steps, and the voltage and current graph, as you can see. Last is the boost charging method, which actually is a combination of the three methods. One is the boost charging method, followed by the constant current and constant voltage. Okay. So next is the battery charging methods, and illustration on the last one. There are actually four levels of charging based on the power and the time that it takes. The first is the domestic or home charging, wherein the vehicle is charged from the power supply available at home, and it takes a lot of time. As you can see, it takes around 8 to 12 hours for charging, and range is 3 to 8 kilometers per hour. The next is charging the same unit with a higher power of 240 volt. The charging time is now decreased to 3 to 4 hours. The next is DC charging stations, DC fast charging stations. This is where the manufacturers have really came in and tried to minimize this experience of minimize this time consumption required for charging. Uh, Here the range is around 160 kilometers per charging, and the time is around 30 minutes. The next is super fast chargers, wherein these are the main players in the market recently, and they have claimed to have reduced the charging time to 10 to 20 minutes. And with in this case, the range is approximately 200 to 250 kilometers. One of the example is Tesla. Right. So the EV, most common EV charging configurations are either classified as onboard or offboard. Onboard, as you know, they are actually placed in the electric vehicle, and the figure shows the typical layout. It has a rectifier followed by the buck converter. Uh, in this design, the main objectives are to lower the footprint and achieve better performance, right? So whatever the voltage generated at the output of the rectifier is controlled by the buck converter in any of the control strategies defined previously. So here, thermal management, current control are the main objectives, and pumping of higher current in the battery is not among the objectives. So the next thing is the onboard chargers. They are designed to meet the desired charging time constraints. High power requirement, high efficiency, superior power quality, and less maintenance are the major constraints. Since it is located off board, weight and size are not at the top of the priority chart. These specifications are conveniently met by using a PWM rectifier instead of a diode pair rectifier. Right, it also helps in maintaining the power quality. And as the charging station is a significant load on any given distribution system, for minimizing the effect, it should be installed at an optimum location in the plant, in the distribution line. Right. So let us see the issues that we have with the current infrastructure when we are installing a powering station, EV charging station with distribution line. Right. So as we know that these distribution line are designed with low overloading low overloading factor, as they have fixed consumption patterns. Adding EV charger would further overload the existing system, right? And if you place a charging station near to the distribution transformer, that would adversely affect the loads that are connected towards the end of the line, right? And depending on the loading of the electric vehicle charging station, the rest of the voltage profile of the rest of the system would be affected. If you place the EV charging station at the end of the line, then the entire line would be affected because of the intermittency of the connected loads. Next is if there are any grid pollution contributed by the charging station, then the all the connected loads to the same grid would be adversely affected. So to as we can see, there are two major problems here. One is connecting this charging station to the distribution line. Second is in everything what happens is irrespective of whatever you do, the distribution line is always affected. So to tackle that, what we can do is we can connect the charging station to medium voltage transmission lines. Right, it has two major benefits. One is the uh, power rating of the loads which are generally connected to the transmission line are very high, so the intermittency of charging station does not affect the line drastically. Second is cost of electricity per unit is less for transmission line compared with the distribution system. The last one, although not an advantage, but it is like there is no hindrance on the power rating of the charging station, which was actually in distribution line. Okay, so this is one of the configuration wherein we have connected the charging station to a medium voltage grid, and as you can see, there is a step down transformer which is being used for stepping down the voltage. And then on the right hand side, this voltage is distributed as an AC line, and each unit has its own rectifier followed by a DC-DC converter. The next thing is obviously distributing the power using a DC link. As you can see, after the rectifier, after the transformer, we have a central rectifier, which actually gives power to all the units. And compared to the previous topology, here less number of converters are there. However, the major concern is with respect to the protection of the DC line. Right, as you can see in both these options, the major problem is the low frequency transformer that we have. So with the advancement in the semiconductor technology, it is possible to replace that low frequency transformer with a high frequency transformer, which is termed as a solid state transformer. It can give you advantages with respect to the performance, size, and weight. And realization of that thing is possible using the advanced semiconductor devices like gallium nitride and silicon carbide. So to explore this territory, the authors have proposed a multi-level SST based system which takes power from medium transmission line and supplies power to three isolated EV charging units. In each of this unit, output of the secondary are connected in parallel. This enhances the power rating of the chargers, so it can be used for charging EV loads like batteries of an EV truck. An illustration of the proposed circuit is shown on the right. As you can see, we are connecting the charging station to one of the phases of a 7.2 kV line to line voltage. Uh, each module consists of four sub modules connected in parallel, so that the power rating at the output can be increased. So if you see now, the switch rating of be the switch rating required in each module is now reduced to 600 volts, so we can use the conventional switches, conventional power rated switches, which has a very good and mature technology, right? So further illustration is shown here. You can see that on the input side of the medium frequency transformer or high frequency transformer, we are using a hedge bridge consisting of bidirectional switches, and what it does is it converts the 60 hertz AC into high frequency AC, so that it can be passed through this medium frequency high frequency transformer. But the problem here that we would be facing, as I have shown in the simulation results as well, is we would be getting inferior power quality performance on the input side too. So to avoid it, we are placing an active filter to eliminate any power quality issues, and the power rating of this active filter is equal to the harmonic content of the grid current. And since we are using only a 5 level converter on this side, we can utilize the advanced silicon carbide or gallium nitrate switches to realize this active filter. So these are the parameters that I have used for the simulation. Herein there are three systems rated each for 100 kilowatt, and I have from a given power supply, I have developed three isolated EV charging units. Okay, as you can see, these are the simulation results, and I have controlled it for different powers ranging from 75% to almost 100% of the output power. But as you can see, there are two problems that we have. First is the power factor is not unity. Second thing, the grid current has significant harmonics. So to avoid that, what I did was we did use an active filter. So here, before the active filter activation, as you can see that the current is disturbed now with the active filter. The current is now sinusoidal in nature, and the harmonics are compensated, and this way we can achieve superior grid performance. And as we have seen in the previous waveforms, the charger gives steady performance for power variations from 0 to 25%. So conclusions are, conventional onboard and offboard structures have been discussed. Potential issues arising due to connection of EV charging station to the conventional distribution system have been discussed in details. Two improvements have been suggested. One is to connect it to the transmission line, and next to replace it with a conventional transformer on the grid side. Since an frequency AC link inverter is used, we are eliminating the high voltage capacitors, but the power quality issues coming up are addressed by a dedicated multi-level active filter. Next is for validation of the suggestions, a novel configuration has been proposed and simulation results have been discussed. Simulation results shows the accurate tracking, as well as with the active filter, power quality issues have been addressed in detail. So these are the references I have used for my presentation, and uh, thank you all for your time.